This is elephant toothpaste. It's this crazy reaction that happens when you mix potassium iodide into hydrogen peroxide. An endothermic reaction means that it releases energy in the process of the reaction, in this case through the form of heat. I had one job. I had to say it was exothermic, and I went and said,
oh, it's endothermic.
It's exothermic. Exo, exit. Energy is released through the process of the reaction. Thank you, that is what I meant. But how does it work? What's actually happening here? And can we do it here at home? I'm Carter McGuire, and that's what we're going to be finding out today. So to understand why this reaction works the way it does, we first need to understand what a chemical reaction is. So a chemical reaction is basically when the molecular structure of a substance gets changed up and switched around and made into a new compound. So when the right compounds are mixed together, they trade atoms or change bonds to make the right compound. So what's happening with elephant toothpaste? Basically, we start with hydrogen peroxide. The chemical formula for that is H2O2. So that means we have 2 hydrogen atoms and 2 oxygen atoms. The other reactant is potassium iodide. So that's 1 potassium atom and 1 iodine atom. So in this reaction, potassium iodide works as a catalyst. That means it doesn't change, it just helps to change the hydrogen peroxide. So basically what happens is when the Ki, potassium iodide, is mixed with the H2O2, hydrogen peroxide, it separates one of the oxygen atoms from the rest of the H2O2, and that leaves us with H2O, water, and O1, oxygen. Obviously, those are all the same atoms that we started with at the beginning of the reaction, but that's because of the law of the conservation of matter. So what that means is that whatever you start with is what you have to end with, because matter can be created or destroyed, only transferred or transformed. Now, the Ki is no exception to this rule either. The reason I didn't talk about it a second ago is because, like I said, it doesn't change, it stays the same. So its molecular structure is the same, but it still has both of the atoms at the beginning and the end. This also ties into our reaction equation. So since we start with H2O2 plus Ki, we end with H2O plus O plus Ki. So a balanced equation for this basically just means you have the same amount of each element on one side and on the other side. This equation works, and this equation doesn't. Now, if we look at our H2O2 plus Ki equals H2O plus O plus Ki, we can see that we already have all the same amounts of each element on one side and on the other. So this equation is already balanced, and we don't have to do anything to it. So now that we know which atoms we're separating, let's think about what kinds of bonds we're breaking. So to keep it simple today and go over a general idea, let's talk about all the chemical bonds that are in hydrogen peroxide. So H2O2 has a molecular structure that looks like this. So from this, we can tell that there are 2 polar covalent bonds and 1 non-polar covalent bond. But what's a covalent bond? Well, a covalent chemical bond is basically any bond between 2 non-metal elements on the periodic table. So once again, I forgot to mention something. So a polar covalent bond is basically a bond between any 2 non-metal atoms that are different elements on the periodic table. But we know that polars are opposites, so that must mean that a non-polar bond is a bond between any 2 atoms of the same element that are all non-metals. But with a callback to our last video, how do we define this reaction as a system of energy and matter? So we start with our components. Now, what I'm going to define as the components is basically the first reactant, everything that gets mixed in with the hydrogen peroxide. So we've got our H2O2. With that, usually people put in some dish soap and then some food coloring. Now, our inputs are going to be everything that's mixed with the potassium iodide. Now, what we're going to do for this, because a lot of people do this, instead of using potassium iodide, you can use dry yeast, because that will give you the same reaction. So for our inputs, we've got dry yeast mixed with a little bit of warm water. Then we've got our outputs, which are basically water and oxygen. So those create tiny, tiny millions of bubbles that just foam up and create this huge cloud of bubbles. The last thing, our boundary. Now, when we're gonna do this, we're probably just gonna put it in like a bucket or something, but I've seen a lot of people use some really weird boundaries, like Mark Rober using his giant pool that he did, or his giant metal beaker thing, but we're gonna use a 5-gallon bucket because we are 15 and on a budget.
Well, actually, you forgot about the process and feedback.
Oh yeah, so our process is basically just pouring the potassium iodide or yeast mixture into the hydrogen peroxide and letting science do the rest of the work. As for feedback, well, if you get a bunch of bubbles, you did it right.
Thank you.
But enough with all this technical talk. Let's grab some buckets and hydrogen peroxide and see if we can do this.
Hey, I don't know if that's a very good idea.
You shut up. Okay, so I did some math and I figured out that the hydrogen peroxide I picked up is 32 ounces, and that translates to 4 cups. which is exactly what I want to use for this experiment. That's probably way too much, and I'm probably going to regret doing this, but I will put on safety glasses, so don't worry. We'll be safe. Dish soap. Nobody ever says how much they use, so we're just going to be generous with it. That's probably good. And then food coloring. Now we're going to take this old wooden ruler and mix it up. All right, that's probably good. Now we'll let that can sit for a minute while we go fix up the yeast. What have we gotten ourselves into? Ew. Okay, so got my safety glasses on. We've got our yeast mixture, and we're gonna pour it into our hydrogen peroxide. So, my calculations are correct. When this cup of yeast water hits that bucket, you're gonna see some serious shit. I don't know if I did this right, but I guess we're gonna find out. Oh, it's bubbling up.
Oh gosh.
Trust. Oh, it's kind of slow. Here, why don't you come over here, Mary? It's not gonna kill you. Pretty slow. Come on, react.
Come on.
Well, so. All right, well.
Dump it.
Okay, well, I mean, it worked for the most part. It didn't blow up or anything, but all right, well, I guess we learned something today.
Oh, that's satisfying.
That's disgusting. Lightly underwhelming. So, what would happen if we took out one of the compounds for this reaction? Well, as you can see, it barely worked as it is. So, no way I just made that. I literally just, oh my God, it landed. I'm actually the best. Anyway, if we took out any one of the elements from the compound, it just wouldn't work. Why is this reaction important? Yo, nerd, help me out.
With pleasure. So elephant toothpaste is not actually important in the traditional sense of a practical significance or utility. It's primarily used as a demonstration of chemistry and reactions and education to outreach and illustrate concepts such as chemical reactions, catalysts, kinetics, and reaction rates.
So what the junk does that mean? It just doesn't matter?
Matter. Well, actually, according to my exhaustively researched findings...
You know what? Don't answer that. Go do my homework or something.
What?
So that's it. In the wildly unlikely scenario that anyone sees this video and actually has questions about it, leave them in the comments down below. With that, I'm Carter McGuire. Thank you all for watching, and we'll see you next time.
Do I really have to do your homework?
Yes, get to work.